Unit 10, Day 3. We're going to focus on reaction types 2 and 3 from Day 2, what we did last time, actually on Tuesday. Anyways, we're going to actually use this like flipping the classroom's supposed to be. You guys are going to watch this for homework, and then we're going to come in on Friday, and we're going to be able to do some of our problems together and discuss some questions you might have. So, what this means, though, two type of reactions, if we go back to the next slide over, next slide previous, you remember the day we were talking about, we learned on Tuesday that there's 4 conditions that you can use to predict spontaneity. If you have an exothermic reaction with a delta S that's greater than 0, it's always spontaneous. Always, always, always. It's always going to be spontaneous because you're always going to get a negative delta G. If you have an endothermic reaction where the delta S is less than 0, it's never going to be spontaneous because you're always going to get a positive delta G. Again, because here you've got a negative value minus a positive value, making it more negative, hence spontaneous. Down here you've got a positive value, delta H would be positive, minus a negative value, the double negative going on, so it's a positive value plus some more. Never are you going to be able to get that answer negative. Now where things can change here is in 2 and 3. We say that this guy is spontaneous when it's at lower temperatures. This guy is spontaneous when he's at higher temperatures. We're going to look at what we mean by lower and higher temperatures in this problem. So, we talked about that. Here's where we are, Unit 10, Day 3. Looking at those 2 reactions we just talked about it. Well, we can approximate what that special temperature is, that at higher temperature or at lower temperature. We can figure out exactly what temperature we're talking about. By remembering that, we said a reaction's at equilibrium. It's not either spontaneous or non-spontaneous when delta G is 0. Well, what that allows us to do is find the exact tipping point, the exact temperature at which the reaction, think about the equilibrium being like where it changes teams. If you cross this way on the equilibrium, you're going to end up being spontaneous. If you cross the other way, you're going to be non-spontaneous. Anyways, so if we set this 0 at equilibrium, delta G equals 0, we can actually solve for temperature. We can solve for temperature by bringing delta H over to the other side. We obviously could have brought delta. We could solve this in many different ways, but anyways, find out that temperature equals, now divide by delta S, and temperature equals negative delta H divided by delta S, or delta H divided by delta S, is that magic temperature, that borderline temperature that tells you when you're going to go from being a spontaneous or a non-spontaneous reaction. Now, what does that mean? Well, for type 2 reactions, it means since they're at lower temperatures, it means the reaction is spontaneous at T, whatever temperature that happens to be, and lower. So let's say you solve for T and it was 10 degrees Kelvin. It means the reaction is going to be spontaneous at 10 degrees Kelvin, 9 degrees Kelvin, so on and so forth, 8, 7, 6, 5. For the type 3 reactions that need really high temperatures for them to take place, if you calculate T out to be 10 degrees Kelvin, again, it's a type 3 reaction, an endothermic reaction, then it would be spontaneous at T equals 10 degrees Kelvin, T equals 11, all the way up to the top of the Kelvin scale. Again, it allows us to know when these guys are spontaneous or not. And obviously we can set a mathematical model to this, and that's what the next slide is all about, how we can make a mathematical, non-calculus based model. You're going to see there's natural logs in there, but we've done the calculus for you. But making a model that can now connect delta G and the equilibrium constant. Because if we think about it, to be a spontaneous reaction, it means products are formed without any outside intervention. The reaction just continues. In other words, it'd have a very high K value, a K greater than 1, because products would just get made. Where if you're not spontaneous, it means the reactants just sit together and no products get formed, or a very, very, very small number of products actually get formed. So you'd have a K less than 1. So there's clearly a relationship between delta G and the equilibrium constant for a reaction. if you have negative delta G's, you're probably going to have an equilibrium constant greater than 1. If you have positive delta G's, you're going to have an equilibrium constant less than 1. And that can be mathematically represented by saying if you take delta G of the reaction, it is equal to negative R the gas constant, we've used him before, times T, temperature in Kelvin, times the natural log of K, the equilibrium constant. So, when delta G is negative, K has got to be greater than 1 for that to work out, because that means the natural log has to be positive, and so K has to be greater than 1 for that to stay negative. When delta G is positive, though, K must be less than 1, because the natural log of something less than 1 is going to be a negative value, which will cancel with the negative R, leaving you with a positive delta G, and it won't be a spontaneous reaction. And again, delta G has to be measured in joules because of the gas constant being in joules. All things need to match up. And we use the gas constant listed in your reference materials, 8.3145 joules per Kelvin mole. We're going to do an example here in a second that's going to allow you to see that in action. But joules per Kelvin mole is what would go in here for R. T would be the temperature you're at, or the temperature you're looking for, depending on if you have K or T. And then K would be your equilibrium constant, which we've spent, weeks now calculating equilibrium constants. So let's look at this example. We want to determine the value of delta G for the reaction from the values in Appendix L. Then, when we use that, calculate the equilibrium constant. Instead of using... So I'm trying to do this trick out of the spot here. Sure what's going on. Okay, trash can. Out of the way. Now we can get back to work. I apologize for that. Anyways, we are going to try and find K. Instead of going through all the trouble we had gone through before, if we have delta G of the reaction, we can figure out what K is. So, how do we actually go? Alright, so here's the problem. Move this stuff out of the way. Well, we can find delta G by taking the sum of the products minus the sum of the reactants, just like we can with delta H, just like we can with delta S. They all have the same exact process. It's that whole idea that they're a state function. It doesn't matter how we get there. The ending point is the same. It's that you can climb a mountain a million different ways, and the view from the top is always going to be the same. But anyways, move that mouse out of the way so you can actually see what's going on. Make this bigger. Perfect. So what we have here are our reactants and our products. So if I'm going to calculate out the delta G, I will simply look those values up. For carbon as graphite, I chose graphite. But carbon as graphite is 0. As diamond, he actually has a value. Carbon dioxide is negative 394.359. And carbon monoxide is negative 137.168. I just look up those values on my selected thermodynamics value chart, which you all should have, and I can see that the units are in kilojoules per moles. I don't want to ignore those units, so I might want to write on all these kilojoules per mole. It's going to come up in a bit. As we said, we've got to have our answer in joules, so we're going to have to change it at some point. I'm going to wait till we're totally done. Now remember, this is our products. That per mole is extremely important because we've got 2 moles right here. So when I'm going to write out the sum of the products, there's only one of them, but it's 2 moles times negative 137.168 kilojoules per mole. That's the products. I'm going to subtract the reactants, which I got two things going on, but one of them 0. Now I of course can include that, say 1 times 0. I'm not going to, it's 0. If it was a value, of course I'd have to have it there. So the only reactant that actually matters is this carbon dioxide. For this example, there's just 1 mole of him, and we said he is 394.359 kilojoules per mole. And through the magic of the calculator, beep, 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 type some buttons in. I end up, hopefully you all end up with the same value. Just like I say in class, who knows. But 120.023 kilojoules. Right? That is for this reaction. The delta G for this reaction is positive. I'm going to make that perfectly clear. Positive 120.23 kilojoules. That tells us a couple things. One, it's positive, so it's not spontaneous. So in the back of my head, I'm saying to myself, okay, it's not spontaneous. When I calculate K here in a moment, it better be less than 1. If it's not less than 1, I messed up because it's a non-spontaneous reaction. It should have a K value less than 1. First thing I'm going to do, though, is change this into joules. By multiplying 1 kilojoule for 1,000 joules, meaning I've got 120,000 joules in this reaction. Well, that lets me know G, and as we said before, delta G is equal to negative RT times the natural log of our K value, and this is what we're trying to solve for, that K value. So I type in my delta G, or place it in there, 120.023 joules equals negative, my R constant comes from my reference packet, 8.3145 times my temperature, 298. Again, at standard conditions, we're always dealing at 298 Kelvin, times the natural log of K. So I'm trying to solve, again, he's Kelvin. And the units on my gas constant are, if we go back to that section, look at our notes, joules. And this is one of the big reasons why we needed to change everything into joules. Joules per Kelvin mole. Let's squeeze that mole in there. I know that's not the easiest for you to see. But that's the unit on the gas constant. What that allows us to do, even though we don't really need units, since K doesn't have units, it's obviously important to keep track of what they are. Anyways, we solve this problem out. Do, again, some magic. Divide by negative 8.3145 and 298 on both sides. And I end up with negative 48.4 equaling the natural log of K. Just like we do log base 10s, natural logs are base e's, so I'm going to raise everything to the power e. E's cancel. Type in on my calculator, there's actually a little e button, most of you know that. I type in on my calculator e to the negative 48.4, and I get a K value of 9.55 times 10 to the negative 22. Whew, less than 1. I'm happy I found the K value just from finding delta H. Oh no, maybe I wasn't recording that whole entire time. Oh, whew, there I am. I was recording. Whew, so you're seeing this right